Today we're going to look at how to create the graphs of the trig functions that we learned about earlier in this unit, the sine, cosine, and tangent functions. And so what we're going to find out is that the functions are written similar to the other functions that we've dealt with in this entire course. Y equals, and then a times sine of bx, y equals a times cosine of bx, a and b both positive constants, and x is measured in degrees. So a couple of things that are important to know about these functions is that they're what are called periodic. It's a repeating pattern. When we see the animation of the sine graph and how it's generated, so this graph has a repeating pattern that continues indefinitely. Each pattern that repeats, as you can see here from 0 to 360 degrees, that's known as one cycle. So if we looked at the sine graph on Desmos and we ran through as far right as you want to go on x, you can see that same pattern repeating over and over again. So if we went left on x, same story. So the sine graph and the cosine graph look very similar. We both see that they have ups and downs, a maximum value of 1, minimum of -1. It looks like one is shift over from the other, and we'll find out a little bit more about those. So for the sine graph, y equals sine of x, when the degree measure is 0, the value of the sine is 0. Its range, its y values go from -1 to +1, and the period, that repeating pattern, is 360 degrees. Similarly for the cosine, this time when the degree measure is 0, the cosine value is 1. It similarly has a period of 360 degrees and a range of -1 to +1. So an important note, we've been talking about degrees, and when we took a look at the Desmos graph, you notice that the x values were 1, 2, 3, 4, 5, 6. That didn't look like it matched up with degrees. That's because the Desmos graph was measured in a unit called radians. You might have noticed on your calculator that you've got a key that says RAD and another one that says DEG, and those are shorthand, DEG for degrees and RAD for radians. We use both to measure angles. The number of radians in the circle is 2 times pi. And obviously there's 360 degrees in a circle, so 2 pi radians equals 360 degrees. And we can use this as a conversion factor. 1 radian is 180 divided by pi degrees, and 1 degree is pi divided by 180 radians. So if you see graphs labeled in radians, that's your conversion. So let's take a closer look at the sine graph. The maximum value of y equals sine of x happens when x equals 90, and a minimum value when x is 270. But because it's a repeating pattern, every 360 degrees, those maximums will repeat. So x equals 450 also equals 1, x equals 810 and 1170. And similarly, the minimum value is at 630, 990, 1350. Cosine will have a similar situation with the repeating values. So taking a closer look at how to graph the sine and the cosine functions. The parent functions, y equals sine x and y equals cosine x, we've already seen those. But what if there's a multiplier or on the value of the function, or a multiplier on the value of the number of degrees? Well, that's going to change the look of our graph. Okay? If you have a multiplier in front of the function, sine or cosine, that's going to change the amplitude. It's going to raise or lower that 1 or -1 maximum and minimum value. If you have a multiplier under degree, that's going to change the frequency, how often the pattern repeats. And you can see that I provided a chart for you in your notes that you can use as a little bit of a cheat sheet. So your first job is to graph the function y equals 2 times cosine of x. So we know that this is going to look like the cosine graph. It's just going to be twice as tall. So when we go to graph this, we're going to go ahead and label our x-axis. Positive 1, negative 1, positive 2, negative 2. And on our y-axis, we're going to go every 45 degrees. So the cosine graph, remember, starts when degree measures 0. The y value is 1. Now because it's 2 times the cosine, our y value is going to be 2. We know that it zeros at 90. Backing up a couple of screens. And its minimum value is at 180. So now that minimum is negative 2. At 270, it has a value of 0 again, and at 360, it has its maximum value. So we've got these 5 points, which look like they're in a V shape. Remember, this is what's called a sinusoid graph. So it's going to have this kind of snake-like feature to it. So the cosine graph, now that we've doubled the amplitude, 2 times cosine of x, it's going to look like this. Our second example, the function y equals the sine of 180 times x. So now that's going to leave the amplitude alone at 1, but it's going to change the period. If you take a look at your chart up at the top of the page, we're looking at the y equals a times sine of x. We have 180 times x, so 180 is our b value. So taking a look, I'm going to have intercepts at 0, 0, and then 180 divided by b, which means there's an intercept at 1, comma 0, and then 360 divided by b, which is 2, comma 0, and then the maximum value at 90 divided by b, 1/2, is where it's going to reach its maximum. So let's go ahead and first lay down the scale on our graph. So the period is 2. So in degrees, I'm going to label this graph with a y value of 1 and negative 1. And on my x-axis, I'm going to go ahead and label 1/2, 1, 3/2, and 2, because this is going to be the period, 2 degrees. So we know we have a maximum at 1/2 and 1, and a minimum at 3/2 and 1, and it's going to have an intercept at 1, comma 0. So let's look at how this is going to go. So for our purposes right now, we're drawing a very similar graph and we're changing the values of the scale. If we were to go ahead and take this, say for instance, to Desmos and take a look at it, let's do a couple things here. So y equals the sine of 180 times x. And let's go ahead and change our graph setting from radians to degrees. And here's what we see, very similar to the graph that we have put together on our pencil and paper graph, where every 2 degrees this graph is going to go through one cycle. So the sine and cosine are very similar. Tangent has a slight difference to it, though. So the graph of y equals the tangent of x, its domain is all real numbers except for odd multiples of 90. At those places, the graph has a vertical asymptote. The range is all real numbers, and its period again is 180. What I'd like you to do now is just pause for a moment with a partner, or if you're watching this on your own by yourself, and think about it. Why would it be that the graph of the tangent function has vertical asymptotes? And why are they located at multiples of 90 degrees? Go ahead and stop the video, think that through for a minute, and you can actually write some notes to yourself on the side of your note page. So let's take a look at the graph of y equals the tangent of 2x. So on the interval of negative 90 degrees to positive 90 degrees, and in this case, 90 over the b value, which is 45. So we know that it's going to have an x-intercept at 0, 0, and then those vertical asymptotes at negative 90 over b and positive 90 over b. Okay, so b is 2, so negative 45 degrees and positive 45 degrees. So in your discussion, as you thought about why the tangent graph has asymptotes, so the tangent can be thought of as the sine divided by the cosine. If you look at opposite over hypotenuse, adjacent over hypotenuse, the tangent is the opposite over the adjacent, so sine divided by cosine. So anywhere where the cosine value is 0, I'm dividing by 0 in that problem, and I end up with a vertical asymptote there. We learned about that a little bit earlier. So I go ahead and I put those asymptote values in there, and these are the odd multiples of 90. So 1 times 90, 3 times 90, 5 times 90, and etc. It also asks us to plot the points that occur halfway between the x-intercept and the asymptotes. And what we find out is the tangent graph is a series of kind of wiggly lines. Let's go and put the tangent graph in radians on Desmos. And this is what we see. You'd have those imaginary boundary lines that would fall right in between your wiggles. So in this case, at 1 radian, roughly, so this all sounds like a lot to process, but the important thing to remember is inside of your notes, there are some step-by-step directions. You'll notice that when the amplitude or the frequency changes, you'll be dividing 90 or 180 or 360 by some value, and that will change where your asymptotes are in the tangent graph. But once you get a chance to practice this a couple of times, I feel pretty strongly that you'll come in with this and it'll fall